Okay, so we found the ground state. Let's just to get an idea about this, let's see what we can do for example, the first excited state. So u1 of x is going to be proportional to, you see we have no guarantee that if we know what u0 is and we apply a plus to it, we are going to get something proportional to u1, but there is no guarantee that the normalization is going to be conserved when I apply an a plus. Okay, so I have a plus u0 is going to give me something proportional to u1. Okay, so let's see what that is. Okay, so a plus times u0 is going to be x over x0 minus I p over p0 times u0, which will be equal to, okay, x over x0 u0 minus I, p is h bar over I, d, okay, p0 d dx u0. Okay, the i's will cancel. So I have something like this. So it's going to be x over x0 times u0. Then I have this term minus h bar over p0 times the derivative of this object. So what is that? That's going to be minus again, minus 2 p0 over 2 x0 h bar times x, okay, times u0 again. Okay, so this is just the derivative of the Gaussian. It brings down this term. So certain stuff will cancel, the 2's cancel, p0's cancel, h bar's cancel. So you see, this is the same as the previous term. So I get 2x over x0 e to the minus, okay, some term p0 over 2x0 h bar x squared. Okay, so this is the form of u1. So qualitatively, what do they look like? Well, u0 we know is a Gaussian. So it does something like this. The first excited state is going to be proportional to, okay, so it will have an envelope u0. It's going to have, again, the Gaussian, but it will also be multiplied by x. So u1 of x is going to do something like this. Okay. Now you can sort of guess what u2 will do. Okay, this has no nodes. This has a single node. This is an even function. This is an odd function. And you can sort of guess that when you get to u2 of x as a function of x, okay, it's going to have two nodes, and we'll do something like this. Okay, so it's again going to have this Gaussian form. Why? Because each time I multiply with an a plus, each time I operate on this function with an a plus, what am I doing? I am multiplying the function by x, and I am also differentiating it, and then I'm just adding them up. Okay, so that's what this a plus does. Okay, it multiplies by x, and it differentiates. In both of those operations, do not touch this Gaussian. So the Gaussian form is still there, and you get a prefactor here in the front, which will be in the form of a polynomial in x. Okay, so the next order thing here is going to be quadratic. Okay, x squared something times the Gaussian. The next order thing is going to be a cubic polynomial times the Gaussian, and so on. Okay, so those are the forms of the solutions. We'll get to it. Okay. So let's look at this problem with the normalization. Okay, so so suppose I have all of these. Okay, so I just want these un of x star, although they are all real, un of x dx from minus infinity to infinity is equal to 1. Okay, that's what I want. Okay, so when I find, for example, what this ground state is, I have to determine that C so that it is normalized. Okay, so I always use and work with an orthonormal set of states. Okay, so I have this. Now let's look at un minus 1. So un minus 1 is given by a minus operating on un, right? So I know that this is going to be proportional to un minus 1. I know that whatever comes out of this is going to satisfy the Schrödinger equation with a lower energy, un minus 1. But the problem is, what is this Cn? Okay? So these UNs are normalized, but when I go from one UN to another using this a plus or minus operator, I am going to get a constant. Okay, so I have to figure out what that is so that my functions are all normalized. All right, so let's just find the magnitude squared of both sides. So what do? I take the complex conjugate of both sides, multiply it with themselves, and integrate. So here I'm going to get a minus un, whatever it is, complex conjugate a minus un, and integrate it, minus infinity to infinity. So that's left-hand side, right? The right-hand side is going to be similarly, okay, let me just put that down, Cn star un minus 1 star Cn un minus 1 dx minus infinity, infinity. Okay, so I have these constants, but I have this un minus 1 integrals. And I have normalized everything. So all of those integrals are 1. So that means this is just going to give me Cn star Cn. Now I want to find out what is going on the left-hand side. Okay. So we'll just prove something like a theorem about what happens when you are operating on something, okay, something on the left-hand side when I have these A pluses and A minuses. Okay, so let me just open a parenthesis here and do some algebra. So I'll say consider the following integral. Suppose I have some f star, which is this piece here, A minus g dx, minus infinity to infinity. Okay, so this is now very general. So let's see what this turns into. I'm going to have an integral minus infinity to infinity f star of A minus, which is, remember, x over x0 plus, okay, h bar over I times, okay, let me do it slowly, otherwise I'll make mistakes, p over p0 g dx, right? Now, let's just expand that piece away. Minus infinity to infinity, f star x over x0. I have an h bar over I there, so it's going to be plus h bar over p0 d dx. Please check my algebra. G dx, right? So h bar over i's, the i's have cancelled and I'm left with p0. Okay? Now, what I'm going to do is I'm going to do this, use this trick and apply, okay, a integration by parts on this derivative object. So what happens? The derivative is going to move on f star, right? And I'm going to get, this is equal to now, minus infinity to infinity. Okay, I have, let me do it like this, x over x0, f star g dx. This is the first integral. But then when I do the integration by parts, I get minus h bar over p0, right? Integral d dx of f star, okay, times g dx. Okay, so I then integration by parts. I move the derivative from g to f, but I now have a minus sign associated with the integration by parts. The boundary terms go to 0 because at the boundaries I am working with wave functions, okay, things like Gaussians, etc., which always go to 0. All right, now let's just try to group these terms again. So I'm going to write this as integral minus infinity to infinity x over x0 minus I, okay, p over p0 f. Am I doing this correctly? Almost, because I put the wrong sign here, right? But what I'm going to do is I'm going to take the complex conjugate of all of this so that I have f star and the plus I. Okay? And multiplied by g dx. Please check my algebra. Is this correct? P is h bar over I minus plus, okay, should be, but I'm not sure. x plus f. Okay, so this is going to be equal to minus infinity to infinity a plus f star g dx. Okay, so what happens is that this a minus here, which is operating on g normally, goes in as an a plus to the front of f. Okay? So, what does that mean? Let's come back to our equation here. We are working on the left-hand side, and we are going to get minus infinity to infinity, a plus a minus un star, okay, times un dx. Okay, what is this a plus a minus now? Okay, it's part of the Hamiltonian. And what does that give me? So I have to do this algebra some other place. So let me move over here. But you can very easily see what a plus a minus is. Okay, in fact, I have most of the stuff over here already. So I'm not going to erase those, but just add something over here. Okay, so h bar omega c. So let me just write it like this. So h un is equal to en un, which means that I'm going to get h bar omega c n plus a half times un. But h itself is h bar omega c, right? N plus a half, not n plus a half, a plus a minus plus a half, right over here, times un. So just compare these two equations. A plus a minus, h bar omega c times a plus a minus is giving you h bar omega c times n, right? So I have this a plus a minus acting on un is going to give me n times un. Okay, so you see this piece here, a plus a minus, is giving you this n, right? So the effect of this a plus a minus is just to pick out the number of the eigenstate. So this thing, a plus a minus, is sometimes called the number operator, a plus a minus. Okay, so this is the number operator. It just means that if you have n times un, it's small n times un. So this n is just a plus a minus and just picks up the n, the number n for you. All right, so over here, I go back to my algebra. This thing here is then just n times un, and n is just a constant. It's the number of this object, and I'm going to get just straight n. Okay, so the left-hand side of the equation becomes n. The right-hand side is Cn star Cn. So we go to this nice convention and assume that Cn's are all real and positive, in which case Cn is just square root of n. Okay, so that tells me that Cn is, well, let me put it this way, a minus un is equal to square root of n times un minus 1. So now if you choose this proportionality constant between un and un minus 1 when you are operating on it by this a minus, then normalization is guaranteed. So if un is guaranteed, what you obtain as un minus 1 is also going to be, okay, guaranteed also. All right, so let's see. What about the other case? Okay, one application of this you can see, okay, one easy way to remember this is that you know that when you lower the index n by 1, when n is equal to 0, you get 0, right? So a minus u0 is 0 because you can't go any lower. Okay, so this n here, this 0 gives you 0. If you are going the other way around, so let me just leave it as an exercise to you. It's just the same algebra, except that you have to work with a plus instead of a minus. A plus un is equal to square root of n plus 1 times un plus 1.
Why don't we have n minus 1 in the upper one?
Where? Over here?
Plus 1. Yes.
Why? It turns out that way.
Yes, but in the second one we have n plus 1. N plus 1. So
just do the algebra. Well, it's not coincidence, obviously, but that's okay. It has to be that way. Why? Let's just do another. Okay, so this one you can see is it has to be proportional to n because you want to get 0. Now, what about how do I check the other one? Just not check, but perhaps verify. We can look at something like okay, so let's just verify. What is a plus a minus un? Okay. Now we know that this is the number operator, right? So I know that this is really equal to n times un, so it has to be n times un. That's what's going to come out. But let's do the following. Let's just first operate with this and get that result, and then we operate again and get the next order result. Okay? So what happens? This is going to be a plus times a minus un. What is a minus un? It's square root of n times un minus 1. Okay? Now I operate on this with a plus. Now what do I get? You see why I need this n plus 1 here. Okay? So when I operate on this by that, I'm going to get another square root of n, okay, square root of n un, which is going to give me n un. Okay, so everything is very nice and consistent. All right, so knowing these things, we can now do lots of, okay, problem solving involving the harmonic oscillator. Yes?
If I have a superposition of some un defined states,
Mhm.
and it also involves U0, then I act on it with A minus. What happens to the probability of the U0 part? Because it kills.
Yeah, but when you're operating on an object with a non-Hermitian operator, anything can happen. Okay, so it's not, you don't expect any conservation laws here. Okay. Okay. So let's look at certain things. Okay, for example, suppose I want to find out, so let me just erase this. Suppose okay, so let's say various expectation values. Now, suppose I want to find the average value of x for a particle in the nth energy level. Okay, I don't even know what the nth object is. Okay, so it first looks a little surprising, but let's just write this down. So what is this? This is going to be un of x un of x. There's a complex conjugate here, but okay, all of these functions are real. Okay, I'm going to get all real functions, so I don't worry about that too much. Okay, so I have something like this. Now, what I can do is I have these relations, which I erased, but I can very quickly replicate here. A minus was equal to x over x0 plus I p over p0, right? And a plus was equal to x over x0 minus I p over p0. Now, what happens if I just add these things together? The momentum terms cancel, right? So I'm going to get a plus plus a minus is equal to 2 over x0 times x. Or I can write x is equal to x0 over 2 a plus plus a minus. I can do a similar thing for the momentum, right? So if I just subtract this term from that term, in that case, I'm going to get 2I over P0. Okay? So if you just do the algebra, you are going to get P0 over 2I A minus A plus. Right? So these are just another way of writing the operators. So what I do is now I just take this x and put it in there. So this is going to be minus infinity to infinity un star of x. Okay, in place of x, I put in x0 over 2, a plus plus a minus un of x dx. Right? Now, what is this proportional to? A minus times un. Yeah, okay, but what the function is? Un minus 1, right? So what is the integral of un minus 1 with un? 0, right? These are all orthogonals. Eigenstates of the Hamiltonian are all 0. So this is going to give me un minus 1, and that is going to give me un plus 1. And both of those integrals are going to give me 0. Okay? So that makes sense. The particle just sits someplace in the well. It's not going anywhere. It's in a stationary state. Now, what happens if I do this with an x squared? What is the expectation value of x squared? Now, that cannot be 0, right? That's the average of positive quantities. So now I have to get a finite result. So I'm going to get minus infinity to infinity un star of x times, okay, x squared. So what is x squared? x0 squared over 4, a plus plus a minus squared un of x dx. So now I can expand this. So x0 squared over 4 comes out minus infinity to infinity un star of x. Okay, a bunch of terms. Square of this. Remember that these are operators and they do not commute. So I'm going to get a plus squared plus a minus squared. Then I'll get an a plus, a minus, and then a minus, a plus. Okay? And un of x dx.
So are number operators, right? A plus, a minus, plus.
Well, this is a number operator. A plus, a minus is the number operator. This is in the wrong direction. Okay, so we have to correct that. What about a plus squared term? What will that give me?
A plus 2.
Okay, un plus 2, so the integral will be
0.
0, right? So this is not going to give me anything. Same goes for a minus, right? Because that gives me a un minus 2. You see, this is so much fun. And you'll have a lot more fun on your next homework. When you go to x to the 4 and x to the 6, this really gets very exciting. Okay, so you have these things. Now, what is a minus a plus?
Again, you're right, isn't it?
Mm-hmm.
N plus 1 minus 1.
Okay, well, what is, okay, let me just, what's a minus a plus? Remember that a minus a plus, commutator of a minus a plus was equal to 1.
So 1 minus 1.
So a minus a plus minus a plus a minus is 1. So a minus a plus is 1 plus, right, n, right? So this is 1 plus n. So this operating on that gives me n. That operating on that gives me n plus 1. So the result of this is x0 squared over 4, okay, times 1 plus 2n. So you see, this operator technique is so powerful. You just do not even know the wave functions, okay? So you don't know the actual wave functions, but you know these relations with operators and everything, which lets you, okay, do all of these things. So if you have un on the left and un on the right, the only terms that survive are terms which have equal number of a plus and a minus in them. Because a pluses raise, a minuses lower. So if you have equal number of a pluses and a minuses, then you are going to get a finite result. Okay, otherwise you get zeros for all of these things. Okay? Any questions? Yes.
This is why I can understand why this un and un plus 1 are orthogonal. I mean, we said ion state, but why they are in state? Because we found lambda 0 and take derivative or something like that?
Okay, we did not yet prove this, but we will prove it that the eigenstates of any actually a group of operators which are known as Hermitian operators, okay, the eigenstates of them are orthonormal to one another, just linear algebra sort of thing. Okay, you have a linear operator which has a certain property, and the Hamiltonian is such an object. In fact, any operator which corresponds to any measurable quantity like momentum, position, etc., they are all a group of operators which are known as Hermitian operators, and eigenstates of Hermitian operators are orthogonal to one another. Okay, so we are going to show that when we get to the more formal part of the course. But just at this point, trust me that these are all orthogonal to one another. Okay. Any other questions? How are we doing on time? Okay, 10 minutes. All right, so maybe we'll also look at the momentum. So I'll do the P and the P squared operators. Okay, so let's see what the average value of the momentum is in an nth state. What do we expect to get? 0, right? This is an eigenstate of the operator. It just sits wherever it is. It's not moving around. So that's what I have. Okay, so that is going to be equal to integral un star, and the P operator was, remember, P0 over 2i a minus a plus u n dx. So very simple. Okay, this is just going to be proportional to un plus 1. That's going to be proportional to un minus 1, so the integral will be 0. So P squared is just going to be the square of this. Let's in fact not repeat something which is trivial because we have already done this, but let's do something like this. What happens, suppose I have, okay, so let's make the problem a little more complicated. Suppose I have a psi x0, okay, some initial condition, so I have a particle which has 50% probability of being in the first or the ground state and 50% probability of being in the first excited state. Okay? Now, the question is, what is the average value of x as a function of time? Now, you see this is a mixed state. It's no longer a state with, a stationary state. So I know that the psi xt is going to have various pieces, 1 over root 2 u0 of x e to the minus I e0 t over h bar, and plus u1 of x e to the minus I e1 t over h bar. Okay, so you see that we have the same sort of things here. Now, let's see what is happening. What we are going to do is we are going to take the complex conjugate of psi xt. Put x in the center, psi xt dx minus infinity to infinity. So what do I get? I get 1 over 2, right? Because I have two factors of 1 over square root of 2. And then minus infinity to infinity. u0 star e to the plus I e0 t over h bar plus u1 star e to the I e1 t over h bar. Okay. X, which is x0 over 2 a plus plus a minus. And then u0 e to the minus I e0 t over h bar. And finally, u1 e to the minus I e1 t over h bar dx. Okay, long integral, but it's not really that difficult. Why? Because I have to make sure that I get the same function on the left-hand side and on the right-hand side. So which ones are they? I have an a plus here. The only way I can get a finite result with this is if I have a plus u0, which makes it an u1 and u1 there. Okay, that's one term that's going to be finite. u1 star a plus u0. Okay, other terms, for example, u1 a plus is going to give me 0 because there's no u2 on the left-hand side. Okay. Similarly, for a minus, the only term that's going to be finite is going to be this, that, okay, and u0 on the left. Okay, all others are going to be 0. So a plus u0, okay, so this a plus u0 is going to be just u1. And a minus u1 is going to be u0. Right? If you figure out the square root of n, etc., square root of n here is, okay, just 1, okay, square root of n here, I need square root of n plus 1, so it's u1. So the integrals, those two integrals are both equal to 1. So I get 1 over 2, the integrals are 1, so I get from this e to the I e1 minus e0 t over h bar. And from the other one, again, plus sign e to the I, okay, minus e1 minus e0 t over h bar times the multiplier x0 over 2. So I end up with x0 over 2 cosine, okay, in fact, omega c, the classical frequency of oscillation, right? E1 minus E0 is h bar omega c. So omega c times t. So the x oscillates with the classical frequency of oscillation back and forth. Okay? So that is an interesting result. Okay, I'll let you go. A few minutes early perhaps, but let's not start anything new at this stage. Okay, I'll see you guys when?